Electrophilic Aromatic Substitution, or EAS for short here, going to be what we're talking about in this first lesson on a whole chapter devoted to the reactions of aromatic compounds. Now, we'll also talk about the side chain reactions on benzene rings, as well as one lesson at the end towards nucleophilic aromatic substitution. But the bulk of this chapter will be focused on these EAS reactions. And in this particular lesson, we're going to go through the general mechanism for electrophilic aromatic substitution. And then we're going to cover the first four major EAS reactions: bromination, chlorination, sulfonation, and nitration, including the specific mechanisms for all four. Now, this lesson is part of my organic chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so before we dive headlong into electrophilic aromatic substitution, I just want to do a little compare and contrast here with electrophilic aromatic substitution, or EAS for short, and nucleophilic aromatic substitution, or NAS for short, that we'll cover at the end of the chapter, just so we see the difference up front before going on here. So in electrophilic aromatic substitution, we are going to be substituting a hydrogen that's on the original benzene here with an electrophile. And so in this case, if benzene's reacting with an electrophile, well, that means that benzene must be acting as the nucleophile, and that will be important later on. Now, in nucleophilic aromatic substitution, we're not replacing a hydrogen. We'll be replacing what we would have thought of as a traditional leaving group, a halogen like chlorine or bromine. It's pretty typical. And we're replacing it with a nucleophile. So when we call it nucleophilic aromatic substitution, it's that we're substituting a leaving group here with a nucleophile. Now, again, if benzene here is reacting with a nucleophile, well, then benzene must be acting as the electrophile. And this will be some fundamental differences between EAS and NAS that we'll point out later on. Cool, so now that we kind of got that out of the way, let's talk about the general mechanism in electrophilic aromatic substitution. Okay, so the general mechanism is actually pretty simple. It's just two steps. What's going to make this more complicated, though, is that benzene is not the most reactive thing. And being aromatic, it's very stable. The electrons are very low in energy. And so for this to work, you have to have an amazing electrophile. And amazing electrophiles just don't sit around on the shelf for very long, so you have to make them in situ. And so we mix reagents that will first react to create this electrophile, and then we can kind of do the standard EAS reaction. So the way this works, once you actually have your electrophile generated, and all the individual reactions will have a little bit different way in which that electrophile gets generated. So but once you have it, then first step is nucleophilic attack. So your benzene is going to come and attack that nucleophile. Cool, attaches right there, leaves us with a carbocation. So, and notice there was a hydrogen on that carbon the whole time, but it's going to be part of the mechanism here in a little bit. So we're going to draw it in, but that hydrogen was there the whole time. So that's the one that's getting replaced eventually by this electrophile. So in this case, we formed this lovely carbocation. This will be a resonance stabilized carbocation. And so I'm going to save some room for a bunch of resonance structures. So, but before we get lost in the weeds, so drawing all these resonance structures often makes this look more complicated than it is. So I'm going to wait for a second. Now, had this just been a regular alkene, like let's just say we take those off for a second, then we'd add the, electrophile to one side, and then we'd have a nucleophile coming back and attaching right here, and we would just do addition instead. So, but big thing here is that we've got an aromatic ring. If we do addition, we're going to end up with a final result of something that is not aromatic. Whereas if we eliminate this hydrogen to restore aromaticity, we'll end up with a much more favorable and lower energy product instead. So in this case, that's why we're going to do substitution instead of addition, because we end up with an aromatic product and it's much more energetically favorable. Addition largely is not going to occur in these reactions in any sort of real competition. It's all going to go through this electrophilic aromatic substitution. So in this case, we're going to have some sort of base coming along. So, and that base is just going to come and deprotonate here. So, and that frees up these electrons to become pi electrons and restore aromaticity to the ring. And so in the end, we complete our substitution there. So again, I did say that we're going to have to show some resonance structures, and so this carbocation is definitely resonance stabilized. And so if we show some resonance structures here, we could move these electrons here. puts the positive charge here, and once again, that's one bond away from these pi electrons, so we can move them here. Cool, and so that positive charge is in principle going to be shared on 3 locations on the benzene ring. So we'll find out that if we have some substituents attached, so preferably in one of these 3 locations, we'll find out it can have profound impacts and even in some cases add additional resonance structures beyond this and make this even more stable. Or in other cases, we'll find out that other groups you might have attached actually might make this lovely carbocation less stable. Now, one thing to note, this lovely carbocation intermediate that is resonance stabilized gets a special name. It is often referred to as the sigma complex. So in your EAS reaction, so this first step is the slow step, because we're definitely going from something that is aromatic, but this carbocation is not aromatic. Notice that carbon right there is sp3 hybridized, and you can't have any sp3s in the ring, otherwise you don't have a continuous ring of overlapping p orbitals. So going from an aromatic reactant to a non-aromatic intermediate, going to have a very high activation energy for step number 1. So that's our slow step. And again, really advantageous then if we restore aromaticity to get our final product. And again, that's why we do substitution instead of addition. Cool, so this is kind of the generic mechanism. The blanks we'll have to fill in is, you know, what's the electrophile for each of our individual EAS reactions and how is it generated? And then who's the identity of the base? But they're all gonna follow this, at least these 2 steps they'll finish off their EAS reactions with. So nucleophilic attack followed by a proton transfer, just a deprotonation to restore aromaticity. Let's take a look at them individually. All right, so here are kind of our 6 fundamental EAS reactions. We've got bromination with Br2 FeBr3, chlorination with Cl2 AlCl3, sulfonation here with what we call fuming sulfuric acid, a combination of sulfur trioxide and concentrated H2SO4, nitration with what we call mixed acid, which is a mixture of nitric acid and sulfuric acid, Friedel-Crafts alkylation, where you've got an alkyl halide and aluminum chloride, and then finally Friedel-Crafts acylation, and that carbonyl group is called an acyl group here, where we form a ketone or in one special case an aldehyde on your benzene ring. So we're going to cover these in sequence and go through the mechanism of all 6 of these. So start with bromination here, and we said before that if you just do this with Br2, it generally is not going to work in most cases. You need this FeBr3, and this FeBr3 functions as what we call a Lewis acid catalyst. And we're going to find out that all of these are going to be catalyzed by some sort of acid, most of the time with a Lewis acid, which is typically a metal ion, like iron or aluminum, as we see in a lot of the cases here. So, but these other 2 here are actually catalyzed by sulfuric acid instead. So, but we're going to have some acid catalysis going on in most of these in one way, shape, or form. So we said earlier as well that you've got to form your electrophile in every one of these cases in C2 before it can react with the benzene. So because it turns out like Br2 itself, it's not a good enough electrophile. We need something more reactive. And so before we can get benzene involved, we first got to form our electrophile. And so what happens first here is one of the bromines in Br2 is just going to attach to iron. That is actually step 1 here. Well, when this happens, you're going to leave one of your bromines positively charged, and then the metal ion will be negatively charged here. So, and in this case, it turns out it's actually this bromine on the end, and I'll draw his lone pairs in. So that actually is now also partially positive due to the positive formal charge of the bromine exome. It's pulling electron density away from making him partially positive. And it turns out he's the electrophilic species. He's the one we're going to attach to. You might be like, well, why don't we attach to the positive one, Chad? Well, again, he's got more bonds than normal already. We don't want to make any more new ones to him. It's this guy we actually want to make the bond to, as it turns out. So let's see the way this works. So for now, we've got our benzene going to get involved. We've now shown the formation of our electrophile. And so now, benzene is going to come and attack that, again, outermost bromine. So that bond to the other bromine breaks. So, and now we've attached and formed our carbocation. We've got our resonance stabilized carbocation formed. We've also got FeBr4 that will be in there as well. All right. So we've got this resonance stabilized carbocation that we're always going to have. And in doing the mechanisms of each individual reaction, I'm going to avoid drawing all the resonance structures for the sigma complex, simply because it's just going to be repetitive and not functional a lot. But again, every time you're going to have a resonance stabilized carbocation that would have 3 resonance structures in every one of the reactions we're going to do the mechanism for. I'm just going to save some time here. But we've done nucleophilic attack and formed our carbocation. We would draw resonance structures as part of any formal mechanism. And then we need a base. And in this case, the base is going to be one of these bromines breaking off. And technically it could be the one that, attached right here, back in this case. But technically it could be any of these in this case. But I'll make it that one. Why not? And we'll come back over here, and he's going to come and deprotonate that hydrogen so that we can free up those electrons to reestablish aromaticity. And so now you're also going to form some FeBr3. This goes back to being FeBr3, but we're also going to form some HBr here as well. And so notice your FeBr3 gets regenerated. We used one of them way back at the very beginning to make our electrophile, but it gets regenerated before we're done, as should be true of any true catalyst. A catalyst is not consumed in the reaction. And this is the mechanism for bromination. Let's take a look and see the similarities with chlorination. All right, so with chlorination here, we see we've got Cl2 and AlCl3. This could also be FeCl3. We can still use iron here as well, just like we use an iron Lewis acid catalyst with bromination. Works with chlorination as well, but AlCl3 is used more commonly, but FeCl3 would work just fine. And first step, again, we've got to form our electrophile. And so just like Br2 attached to FeBr3, we've now got Cl2 attaching to AlCl3. And once again, it's actually this chlorine on the end that is the reactive one as an electrophile. We're going to attach to him, freeing up these electrons to go back to that chlorine so it doesn't have a positive formal charge anymore. So that is actually the species, the electrophilic species that benzene will react with. So benzene come and attach to chlorine and bond to the other chlorine breaks. Whoop. We're not going to have that aromatic for a spell here. Once again, this would be a resonance stabilized carbocation. We're not going to draw out all those resonance structures. And then we also form some AlCl4. And just like in the last instance, one of these chlorines is going to break off instead of a bromine. And bond to that hydrogen, that frees up these electrons to restore aromaticity. So we're also going to form some AlCl3. We've regenerated our catalyst, not consumed, and then also formed some HCl as well. Cool, exactly analogous to what we saw with bromination here. So free radical, electrophilic aromatic substitution, chlorination, exactly analogous to electrophilic aromatic substitution for bromination. All right, now we're going to move on to sulfonation here. And recall the reagent is fuming sulfuric acid, a combination of sulfur trioxide and concentrated sulfuric acid. Now, one thing you should note is out of all of these, this is the one reaction that ends up being reversible and with dilute sulfuric acid. And some will actually show heat as well. With or without the heat is how it might be presented in your class, but it is reversible. With dilute sulfuric acid, you can desulfonate as well. So let's take a look at the mechanism here. In this case, most commonly, this is actually the one reaction presented with a ready-made electrophile. Sulfur trioxide. Some will show it actually as being protonated right off the bat. You'll have to protonate it first from the sulfuric acid, but most textbooks actually show it just as the electrophilic species being the sulfur trioxide itself. And so we'll do nucleophilic attack on the sulfur here, kick electrons out to any one of these oxygens. Cool, and then we just simply need to deprotonate this hydrogen, and our base in this case is going to be the conjugate base of sulfuric acid. So bisulfate here. That'll free up these electrons to restore aromaticity yet again. So, and then from here we just form some sulfuric acid here, and there's solutions chock full of concentrated sulfuric acid, so even if we didn't, we'd have a bunch of it anyways. So, and then we'll just deprotonate one of these sulfuric acids to protonate this guy and form our sulfonate group, our sulfonic acid group, if you will. Cool. And this right here is what we abbreviate as the SO3H group. So whether you've seen it drawn out, the sulfonic acid group, or just see it drawn as SO3H, you should be prepared to see it both ways. All right, now if you look at the actual reverse reaction here, so from this guy, we'd simply just go backwards and deprotonate. And I'll pick up the mechanism from that guy right there. So, and in this case, when dilute sulfuric acid, we're going to have a fair amount of hydronium around. Some mechanisms show this as just H+. So it'll actually show us the most likely source of that, and that's the H3O+, the hydronium here. And we're just going to simply protonate. So this guy. Now we've added that H right there, still have a carbocation here. So, and then from here, we'll kind of undo exactly what we did when we attacked the sulfur trioxide to begin with, kick these electrons out to the oxygen. Well, those electrons are going to come right back in, reform a double bond to the sulfur, causing this to break off and leave, and go back into being a pi bond. So exactly the reverse of essentially what we did in sulfonation. And we get back to having our SO3 and just plain old benzene. So cool, if they're going to leave something out, it is this desulfonation mechanism. So, but for some of you that would still have this presented in your course, we've covered it here. So the next one we're going to look at is nitration here. And nitration, we use mixed acid as the reagent, which is a mixture of nitric and sulfuric acids here. And sulfuric is the stronger of the two acids. It's going to function as the catalyst in this case. And just like normal, we've got to generate the electrophile before we can react it with benzene. And so it turns out, again, sulfuric acid and nitric acid are going to react with each other. And with sulfuric acid being the stronger acid, what's going to be weird is that nitric acid, which is itself a strong acid, is actually going to act as a base. So sulfuric acid is actually going to protonate nitric acid. Now, I usually ask my students in person, so where would be the most common place you'd probably want to, end up protonating the nitric acid here? So, and in this case, the highest energy electrons are on that lovely oxygen. Technically, it's shared between the two oxygens. They got a negative charge. So, and that would be the most likely place to get protonated. The problem is it doesn't lead anywhere. And so, kind of like if I, invited you over for a party and I said, hey, I need you to go get some ice. And you're not familiar with my neighborhood, and so you're on your way to go get some ice, and you turn into a cul-de-sac. Well, that doesn't lead you anywhere, so what would be the first thing you'd do right after turning into the cul-de-sac and realizing it doesn't lead you anywhere? You'd make a U-turn and turn out. And so same thing here. If you end up protonating this oxygen right here, it doesn't lead anywhere, and so the only thing you could really do is then reverse course and unprotonate it. So, or deprotonate it, I guess, in this case. So it turns out, I'm only explaining that because if you're wondering after the fact why we didn't protonate there, well, I mean, again, it's the most likely place. It probably happens all the time in the solution. It just doesn't lead anywhere, and so it's reversible and would come off. But we're going to end up protonating this oxygen over here instead. And again, it's not the most likely place to protonate, but it will actually lead somewhere. All All right, so we get this lovely species, and it should look very familiar to what you did with an alcohol. Is an OH a good leaving group? No, it's not. How did you make the OH of an alcohol a good leaving group? You protonated it. And once it became water, it became a much better leaving group. And that's what's going to happen here, is it is actually going to leave. Now, that's not the only thing that's going to happen. It turns out simultaneously, we typically show pi bond formation between the nitrogen and oxygen there as well. That way we don't violate the octet rule on that nitrogen, which would be a really terrible resonance structure to draw. Cool, and so in this case, you are going to form some water when it leaves, but you're also going to form this lovely species right here, so NO2 with a plus charge, and this is your electrophilic species. Again, having a positive charge, great electrophile. That's what actually is now going to react with benzene here. So 2 steps to form our electrophilic species in this one, and this is one of the more complicated one that students struggle with a little bit, but it's just those 2 steps, and you can relate it to what you did with alcohols, protonate the OH, and then have it leave, and there you go. All right, so we'll do nucleophilic attack. Doesn't matter which one of these oxygens we kick the electrons to. All right, we get our lovely carbocation, and again, we typically draw this hydrogen in because we're about to use it. That hydrogen's been there the whole time, though. This is also a resonance stabilized carbocation, but once again, I'm cheating, and I'm not drawing all the resonance structures, but there would be 3 resonance structures. So, and now we need a base to come in, and in this case, you got really 2 options. You've got the HSO4- or the H2O, and you'll see either one potentially used in textbooks. So, in this case, I'm going to use the HSO4-. But like I said, you see textbooks do it either way. And that allows us to reestablish aromaticity. Cool, and regenerate our H2SO4 catalyst there. Cool. Also wanted you to see that, we've written it as an NO2 right here, but a lot of students sometimes don't realize what an NO2 group, the nitro group, looks like right here. So, but notice you got a positive formal charge on the nitrogen and a negative formal charge on one of the oxygens. And again, by resonance, technically it's actually shared between both oxygens, but this is one of those resonance structures, and we typically only draw one. But I just want to make sure you see that there is a positive formal charge on that nitrogen. That'll be important later on in the next lesson. Cool, but that's the mechanism for nitration. Now, if you found this lesson helpful, would you consider giving me a like and a share? Pretty much the best thing you can do to make sure other students get to see this lesson as well. If you are looking for the study guide that goes with this lesson, if you are looking for practice quizzes on electrophilic aromatic substitution and reactions of aromatic compounds, if you're looking for a final exam rapid review or practice final exams, check out my premium course on chadsprep.com.